suppose G is a function whose domain is the closed interval from A to B, and whose codomain can also be taken to be that same closed interval. This is really important. This is essential, in fact, to specify that as the codomain. It's not that you couldn't say the codomain is all of R, but we want to emphasize that the codomain can also be taken to be the same interval as the domain, because we're trying to say the outputs are always in the same interval as the inputs. That upside down A means for all, if you've forgotten or if I haven't told you. G of X, the output of G, is in the same interval from A to B, no matter what X is in that same interval. And we're also assuming it's continuous on the entire interval from A to B, again, expressed compactly with that notation. G is an element of that vector space. The conclusion is, we saw this on Tuesday, G has at least one fixed point in the interval from A to B. In other words, there exists a point P in the interval such that G of P equals P. The book has a formal proof of this, and I was thinking I would like to do the formal proof and give you insight about it, but I think what I'll do instead, for sake of time, is I'll just talk about the proof, and then you can read it to see the details. It is a proof you should be able to do. It's not super hard, though it is a little tricky for people the first time they see it. So what's the idea of the proof? So let's draw a generic graph of a function whose domain is the closed interval from A to B, and whose codomain can be taken to be the exact same interval on the y-axis here. So the line y equals x does go through the points with coordinates AA and BB. There's y equals x. And in fact, it's helpful to draw a box, a rectangle, in for, you know, how you'd see it on a calculator. X going from A to B, X min is A, X max is B. Y going from A to B, Y min is A, Y max is B. We don't know what the function G looks like. We just know it's continuous. And we also know, most fundamentally besides the continuity, that the outputs are always between A and B. The graph is not going to be up here. It's not going to be down there. It's got to be in this box over the entire interval. It could be doing something crazy. Continuous functions can do crazy kinds of things. I think I do want to show you examples of crazy continuous functions next week sometime. They can oscillate, in fact, infinitely often, but the continuity forces you to cross this y equals x line at least once, maybe more than once. So there's G of x. You're forced, you would say visually, by the continuity of G to have to cross that line. And also, again, the fact that the codomain is the interval from A to B. The image of this function, of this interval under this function, would be a subset of this. Or range, if you want to use the word range, but I like avoiding the word range. Except in calculus courses where the textbook forces me to use the word range for homework problems. Okay, it should feel, because of the picture, like probably an application of the intermediate value theorem. But the intermediate value theorem doesn't talk about crossing diagonal lines. Doesn't talk about crossing diagonal lines. It talks about crossing horizontal lines. So the main issue of the proof is, how do you convert crossing a diagonal line to crossing a horizontal line? What's an equivalent problem? And the equivalent problem is to define a new function, we could call it f of x, to be, say, g of x minus x. Like we've been talking about, right? When we think about if G was the cosine function, and we're after where does cosine of x equal x, that was our main problem from Tuesday's class, that's equivalent to cosine of x minus x equaling 0. The function cosine of x minus x had a root exactly where cosine of x equals x. G is continuous, and x is continuous, therefore f is continuous. G continuous, and the identity function x continuous, I won't write that down, implies that f is continuous over the entire domain on the closed interval from A to B. Moreover, f of A is g of A minus A. How does the condition about the outputs of G always being in between A and B come into play in the proof? It's got to come into play in some way. Comes into play in saying this has got to be greater than or equal to 0. Right? Because G of A has to be bigger than or equal to A. I mean, it could equal A, although if it did equal A, then we'd be at a fixed point already. And f of B is G of B minus B. That's got to be less than or equal to 0. But wait a minute. In the statement of the intermediate value theorem, f of A and f of B should be different. But couldn't they both be 0? Well, yes, again, they could both be 0. But if they were, we'd again already have fixed points. And we'd be done. That's kind of the easy case. So the harder case is though neither A nor B is a fixed point. Harder case in quotes, it's not that hard. If neither A nor B is a fixed point, FP for fixed point, then f of A is strictly positive and f of B is strictly negative. So if K is 0, there's got to be some C between A and B so that f of C equals 0. Right? That's positive, that's negative. The IVT implies there exists a C between A and B such that f of C equals 0. The 0 is the K from the intermediate value theorem. But you don't have to use the letter K in your proof. And if f of C equals 0, that equation is equivalent to G of C minus C equaling 0, which is equivalent to G of C equals C. In other words, C is a fixed point of G. Okay, so that's the essence of the proof without being real formal about writing it up. The book does a formal proof. We have to set it up to be able to apply the intermediate value theorem. Now, of course, you could have said, well, couldn't we just come up with a new theorem that says functions like this have to cross y equals x and call it the slanted value theorem or something? Well, essentially, we're doing that in proving this in this way. The intermediate value theorem, when you take real analysis, is a harder proof, actually, than this. It's a harder proof and it requires a real analysis heavy hitter called the completeness axiom or least upper bound property, which also is related to concepts called supremum and infimum, or infimum if you prefer. And that's those are really hard concepts right near the beginning of the course. And you don't get to proving the intermediate value theorem until like a month in or something. You have to understand limits and continuity first. Maybe it's even 2 months in. You remember? 2 months in. You don't get to proving the intermediate value theorem, which we just used here, till 2 months into the course, because you got to do all the spade work first. But once you got the intermediate value theorem, then you have this slanted value theorem, so to speak, this fixed point theorem that can be proved relatively easy using the intermediate value theorem, using this trick effectively. What else do we have in the book? This is not the only thing. Theorem 2.3 part 2 says if in addition, meaning Same hypotheses as before, but now we also assume G is differentiable on the open interval. And a constant K between 0 and 1 exists, making the derivative of G evaluated at X less than or equal to K for all X in that open interval. Then, in fact, not only is there a unique fixed point, it's unique. There's exactly one. It's not labeled this way in the book, but some people say in this situation, when G has a derivative whose absolute value is small, K is a small number, right, between 0 and 1. It's positive and it's less than 1. In this kind of situation, G is sometimes called a contraction mapping. Contraction mapping, because it's kind of like shrinking the interval from A to B. It's guaranteed to shrink it, so to speak, because its derivative stays small in absolute value. It's contracting it. So when you've got a function, a continuous function on a closed interval that's contracting into that same closed interval, then there's got to be a unique fixed point, exactly one value of P, such that G of P equals P. We already know there's at least one. How do you know there's no others? In my picture that I drew for the first part, I'm leaving the slide up here so you can keep writing if you want. I drew a function that oscillated a lot and had more than one crossing of y equals x. It had 3, in fact. My function had a derivative that got relatively large in absolute value in a couple spots, number of spots. Either positive slope or negative slope. So my function that I drew did not satisfy this contraction mapping condition. What's the proof of this one? Again, I don't want to take the time to do a formal proof. It's in the book. But let's again talk about the idea. So again, my derivative of this function gets big in spots, number of spots. In particular, it's relevant that it's large in absolute value there, there, and there, you know, where it actually has fixed points. But if it gets big in absolute value, there's no guarantee that you've got just one fixed point. You could have more than one. If I were going to draw a function whose slope never got too big positively or negatively, it would be, you know, almost a horizontal line, so to speak. You'd be forced to cross y equals x just once. Once it crosses, it wouldn't be able to change fast enough to cross it again, because y equals x has a slope of 1. That's the intuition, why it can't cross more than once. But the formal proof involves the mean value theorem. We know there's at least one fixed point. How do we know there's not more than one? How about argue by contradiction? We did that for proving the square root of 2 was irrational, meaning not rational. Assume it was rational, get a contradiction. That's how to prove in general something's irrational, because irrational by definition is not rational. How do you prove there's a unique fixed point? Pretend there are 2. Try to get a contradiction. Assume to the contrary. So this is for the contraction mapping part of the theorem. Assuming to the contrary, or I should just say assume. Assume to the contrary that P and Q are fixed points with P not equal to Q. So they are distinct inputs, or distinct fixed points. They are both in the interval from A to B, right? That's the situation. P not equal to Q. We could do it without loss of generality, assume P is less than Q here. It's not really necessary to do, but maybe a little easier conceptually. WLOG in a math proof means without loss of generality. we could assume P is less than Q. Why? Because they're just arbitrary symbols anyway. Q's less than P would be the exact same argument. The book doesn't bother with this, but it doesn't hurt. They just say they're different. What does the mean value theorem say? The mean value theorem applied to a function, a continuous function, on, say, the interval from P to Q, where the function is more than continuous, it's also differentiable. Fixed points. FP's fixed points. I should say of G. With the mean value theorem, you've got a function that's continuous on some interval and also differentiable on that interval, or you can get away with actually differentiable on the open interval from P to Q. You don't have to include the endpoints. Says there's got to be some value of C between P and Q in this case, where the slope of this secant line equals the slope of this tangent. The secant line between the 2 points in the graph and the tangent line have to be the same. Those have to be parallel. The textbook, I'm so happy, for this point between P and Q uses my favorite Greek letter. You remember this from Prob Stats, Xi, squiggle, which is beautiful when you make it slow and also can be beautiful if you make it fast, though I'm not always good at making it fast. Yeah. Okay, you can get better with practice. Squiggle. Okay. Oh, it's hard when you're doing it in front of people. Okay. The mean value theorem implies there exists a squiggle between P and Q, Xi, such that G prime of C equals G of Q minus G of P over Q minus P. Now, the book finishes the argument from this point a little differently than I'm going to do here. My way is quicker, you might say better. You might say better. Q and P are fixed points of G. Hey, that would mean G of Q equals Q, G of P equals P. This fraction equals 1. Right? They're fixed points. G of Q equals Q, G of P equals P. I get Q minus P over Q minus P equals 1. But wait a minute. That can't be right. G prime of C equals 1. That would contradict the assumption in the theorem that the derivative is always less than or equal to K in absolute value, where K is less than 1. Done. Contradiction. It's not a star. It's 2 arrows pointing at each other. Contradiction. And what does that mean? It means we're done, because it means the assumption that P and Q are different fixed points must be false, so there must be just one fixed point. Now, again, the book gives a different argument. Again, I'd say this one maybe is superior because it's just quicker. They take this equation and rewrite it based on this. They write, well, they switch the order of P and Q around, but it's not a big deal. The distance between Q and P, which is the absolute value of their difference, since Q and P are fixed points, this is the same as the absolute value of G of Q minus G of P. That's going right there. But then using this equation and multiplying both sides by Q minus P, that's the same as this. The absolute value of the product of two numbers is the product of their absolute values. and then use the inequality and the assumption in the theorem. The derivative at c must be less than or equal to k. But hey, k is less than 1. And so we get, in the end, that the absolute value of q minus p is strictly less than the absolute value of q minus p. A number is less than itself. Impossible. There's your contradiction. A number can't be less than itself. So theirs takes a little more work, so you might say it's not as good. However, it's still a worthwhile thing to think about it this way, because in the next theorem's proof, it is essential to use this kind of reasoning. And what's the next theorem? It's this one. Down here, theorem 2.4 and corollary 2.5, which I combined into one theorem here. If, in addition, meaning every other hypothesis is satisfied, G maps the interval from A to B into itself. G is also a contraction mapping, so the absolute value of its derivative is always less than or equal to k, where k is less than 1. And we now have an initial condition, a seed, P0, and we recursively define a sequence, Pn, to be G of P sub n minus 1, so we're doing function iteration. Then that sequence that we've created converges not only to a unique fixed point in, well, okay, it converges to the unique fixed point of P and A to B, which we already know exists. So again, the new thing here is that this recursive sequence converges to P. That's the new thing. We already know the unique fixed point exists, but now we're saying it converges to P. And moreover, we can get a couple different bounds on the absolute error. One bound that can be found is that the absolute value of Pn minus P, the absolute error, is less than or equal to k to the n power times the maximum of P0 minus A and B minus P0. Now that's kind of complicated looking. Draw a picture to help you. Your interval is A to B. You're pretty sure the fixed point's in there somewhere, but you don't know exactly where. Of course, you could graph it with technology to see pretty good where it is, but pretend you don't have technology. Maybe it's there. Maybe that's P. But you pick a P0 over here. Maybe P0 is over there. This distance right there is P0 minus A. And this distance right here is B minus P0. Which of those is bigger? It's B minus P0. So for this picture, that distance would be the maximum value that you see in the inequality. Multiply that by k to the n, where k is the same k as before. The absolute value of g prime of x is always less than or equal to this k, where k is between 0 and 1. Maybe k is, for your example, is 0.8 or something. The point is, the inequality, the term on the right can be computed easily. You pick your P0, I mean, probably you'd pick it to be the midpoint anyway, so these differences would be the same. But if you don't pick it to be the midpoint, pick whichever of these is bigger, multiply it by k to the n. And that's a guaranteed upper bound on this absolute error. And then if you can figure out how big should n be to make this less than, say, 0.01, then you could figure out, again, a guaranteed minimum number of steps to get within a certain error tolerance. This other inequality is true as well, though its proof is harder. You still involve a k to the n, but you also effectively have the distance between your initial guess, P0, and the first iteration of G, P1, divided by 1 minus k. Proof of this one's harder than the proof of this one. Which inequality is better? It would depend on the situation. You'd have to try examples and see which one's better. Maybe it's different. I haven't tried enough examples to know in general which one's better. Try some examples and you'd see. P1 minus P0, if you picked a good value of P0 that's close to the true root, P1 minus P0 you would hope would be a pretty small number. And if K is pretty small, like 0.1 or something, then 1 minus K, relatively big, like 0.9, you're dividing by a relatively big number. This certainly could be a small value. And if you did something weird and picked A and B to be far apart, then these numbers could be big. But of course, you could pick A and B to be smaller or closer together. So, I mean, you could make this part of this inequality smaller by how you pick A and B. The proof of this one is in the book and not too hard to follow if you are careful and thinking about it, and you should. Proof of this one's also in the book, but it's harder to follow. You can do it, though, if you set your mind to it. Hey, it rhymes. You can do it if you set your mind to it. That was my stomach. You can do it if you set your mind to it. Maybe you didn't even hear that. Should you do it? I think you should. If nothing else to it, then to try to give this book some love. Maybe not many people give it much love. Because I know from experience in reading this book, it's not the easiest read. But if you set your mind to it, you can do it. You can read the book and get benefit out of it. And I think it's a worthwhile thing to do. It also happens to review the formula for geometric series. Comes into play in the second proof. That's nice to see. And is another thing to know that does come up actually in later proofs too. So it's a worthwhile thing to do. How do you apply these theorems? In a given situation, you have to check these conditions and see if they hold. That in general is not an easy thing to do, and we're low on time. Let me just refer you to the book's examples. You should, in fact, there's one main example you should study, or they call it illustration. You're trying to apply the theorems to different functions in this illustration that are supposed to have the same fixed point, I believe, because they refer to the same, they're different G's for the same F, right? We talked about this on Tuesday, and you had homework problems about this. F of X equals 0, you're trying to find the root by finding a G whose fixed point is the root of F, and there were different ways of doing it. So these are a bunch of different G's that are all supposed to have the same fixed point, but not all of them work to find that fixed point by function iteration. The first example does not work. The second example evidently does not work by the reasons they give here. The third example evidently does work. When you study this third example, you should draw pictures. Don't study this without drawing pictures. They evidently can apply the theorem. Draw pictures to help you understand. Draw graphs to understand why they are doing these calculations and explaining things the way they do. There's a fourth and fifth example as well. Evidently, the fourth example works. Evidently, the fifth example works as well, but they don't say why. Because that's about Newton's method, actually, which I suggested that you read about also this morning, though we haven't had time to actually talk about it in class. And I think that's enough for today. I wanted to talk about Newton's method, but we need more than 3 minutes or 2 minutes now. Okay? So have a good day.